Sir.
You are using HOD email ID, it seems. HOD Mechanical.
No, that is my email only.
RGM HODME?
That is department mail ID.
Oh, acha, okay. I thought you were a mechanical HOD.
Hello, good morning, sir.
Namaskar, good morning, sir.
Sir, is Vaishnav Devi University is a deemed university, sir?
No, it is not a steamed university. It is a state university.
Sir, its branches are there in India, in some other state, or is it the single one?
No, it is not. There is no branch in the other apart from some video cutter.
Because I heard this name, university name, somewhere in Chennai, sir. Is it there?
No, please, you can share the details. We will take a legal course of action against those people.
Okay.
No, is there details? Please, you can provide us register at smvdac.in. So let me take a legal course of action against those people.
No, not sure, but I heard the name like Vaishnav Devi University somewhere. I heard, sir.
No, if it is anything you come across, please you report to us, sir. We will take legal action.
I thought, sir, like this. Suppose V8 is there, no, sir. V8 is there in Chennai, Vellore, Bhopal, like that. I thought.
No.
Like that branches are there? No. Okay.
No, it is not a private, no? It is a state university. It is from the J&K state.
Okay. Is that ready, sir?
Sir,
Now we can start, sir. 10:30.
10:30 అయిందా సార్?
Otherwise, we will wait for participants for 10 minutes.
17 members are joined, including myself and expert.
Okay.
Sir, shall we start, sir?
Yes, sir. Please proceed.
Yes, sir. So, good morning to today's speaker, Dr. Ishwaramurthy Muthuswamy sir, and my dear participants. So, I welcome you all for the faculty development program on renewable energy intervention in industry, domestic, and commercial applications. So, this is the last but one day. That is 11th day of FDP. That is morning session. So today we have expert Ishwaramurthy sir, who is a professor from Mata Vaishnava Devi University. So sir is going to give an expert talk on solar thermoelectric power generation. So before handovering the session to expert, so let me introduce him. So Dr. Ishwaramurthy Muthuswamy, Professor Mechanical Engineering, Sri Mata Vaishnava Devi University, Katra, Jammu and Kashmir. And also sir is a registrar of Mata Vaishnava Devi University. So sir did the PhD in solar thermal engineering from National Institute of Technology, Tiruchirappalli in the year 2011. And a master's MTech in energy technology from Pondicherry University in the year 2004, and a Bachelor of Engineering in Mechanical Engineering from Bharatiyar University 1995. So sir worked as a lecturer in 1996 to 2001 at Nanjappa Institute of Technology, Coimbatore, and then moved to the another college, Adiyaman College of Engineering from 2003 to 2007 as assistant professor, and then in the same college, sir worked as a professor from 2011 to 2014, and then 2014 to 2018 again sir moved to the another college, ACS College of Engineering, Bengaluru. So from 2018 onwards, sir is working in the Sri Mata Vaishno Devi University, Jammu Kashmir. So sir's research interests are solar photovoltaic, thermoelectric energy systems, hybrid energy systems, solar thermal system coupled wind energy generator, thermoelectric power generation embedded on solar thermal collector, and waste heat energy recovery, energy and exergy analysis, energy efficient and pollution free cooking stoves, hydrogen generation from renewable energy sources like solar, wind and biomass. So research projects undertaken around 6 lakhs worth of projects, and guided one PhD student, and 7 students are doing the PhD under the guidance of Ishwaramurthy sir, and 5 MTech students completed, and delivered 14 lectures in various institutes, IITs, and sir is also a member in editorial board, International Journal of Energy Engineering, World Academy of Publishers, International Journal of Integrated Energy System, serial publishers, and then International Journal of Environmental Research and Development, Research India publishers. Sir also a reviewer to the many journals, International Journal of Solar Energy Engineering, American Society of Mechanical Engineering publications, ASME publications, International Journal of Applied Physics letters, American Institute of Physics, International Journal of Sustainable Energy Technologies and Assessments, elsewhere publications, International Journal of Energy Conversion and Management, elsewhere publications, International Journal of Applied Thermal Engineering, elsewhere publications, International Journal of Sustainable Energy, Taylor and Francis publications, International Journal of Exergy, Ender Science publications, and then International Journal of Renewable and Sustainable Energy, American Institute of Physics, Journal of Renewable and Sustainable Energy, American Institute of Physics. Sir published 24 international journals, 1 national journal, 18 international conferences, and 12 national conferences. So thank you, sir. So this is a brief bio sketch of Ishwaramurthy sir, available with us. So first of all, we would like to thank Ishwaramurthy sir for accepting our invitation to give an expert talk on solar thermoelectric power generation. So with this, I am requesting Ishwaramurthy sir to hand over the session.
Thank you, Dr. Siddhareddy sir, for your introduction about me. Thank you so much for giving nice introduction. I also thank Dr. Shivareddy sir for providing this an opportunity this morning today. So very good morning to all my participants, all my colleagues, and the management of Rajiv Gandhi Memorial College of Engineering and Technology, Nandyal. Today, I'm going to discuss about the topic solar thermoelectric power generations. So probably many people are talking about solar thermal power plant, solar photovoltaic power plant. Probably this topic, it is coming up in the research community, solar collector association with thermoelectric, solar devices associated with thermoelectric devices. So it is similar concept of a hybridized solar collector with thermoelectric or integrate solar collector with thermoelectric devices. So that is a concept here. The problem is why we are integrating the thermoelectric thermoelectric into solar collectors. The solar collector or solar photovoltaic having a conversion efficiency is limited, but it has some drawbacks. The drawbacks in solar photovoltaic in the form of what we call an excess heat or an optimum heat of cell material. It is in major issues where the excess heat can be recovered and can be used for the power generations. So my talk, it's connected with some basic fundamentals about thermoelectric and what are the various applications connected to what we call it, this topic of solar thermoelectric power generations. So I affiliated to the University Sri Mata Vaishnadevi University. I'm professor in mechanical engineering. I think other things about my introduction, Dr. Siddharthi sir is given clear information about me. So with that, so I like to start my sessions. Yes. Now we like to move forward to the background. The clean energy sources in its government agencies, the government, the local or private, they're talking about clean energy sources. It is a great concern for the last two decades. Then why? What is the reason? The problem of greenhouse gas emissions, and develop this cost-effective renewable energy technologies demanded for more and more to avoid dependency of fossil fuels, to reduce the outcome of greenhouse gas emission from the combustion of fossil fuels. So the cost-effective renewable energy is most important topic. So in this, the renewable energy, the solar energy is the supreme power of other sources. It is a mother of renewable energies. Still, it has some disadvantages on the cost of material, about the surface, and also the problem of the nighttime functions, since it is available in 8 hours in a day maximum, and remaining of bright sunshine hours, we are not receiving it in a nighttime at your locations, at your site. This is in one issue. The direct energy conversion attracts the researchers due to simple in constructions and easy to fabricate. Where the thermoelectric, one of the devices, when if you are assisting the solar devices with thermoelectric generator, it is more attractive options as energy conversion is concerned. Completely green energy conversion, it is going to accept large spectrum of solar radiation to convert the solar radiations. So convert the electricity. That is main special features, main attractive features. The people shall start working on the solar thermoelectric. We like to take some background, where the conversion of solar radiation into electricity, probably other previous speakers already had a talk, probably it is in solar thermal collectors, where the heat exchangers, it is an indirect method, how the electricity is going to be converted. It is the heat engine route, heat engine cycle, medium and high power capacity, more than 100 watts, 100 kilowatt. It is for the indirect method, the capacity. Where the direct method, solar photovoltaic panels, it is going to be used. It is the less than 1 kilowatt. It is what we call that in one very comfortable things. 1 minute, sir, I will join. Sir, I'm in online classes, sir. I will join at 12:30. Good morning. Acha, okay. Acha, okay, sir. Okay, take care, sir. Take it. Thank you. Hello. Yeah. So, thank you for patient waiting for time. So here, what we call it an direct method. The solar photovoltaic panel, it is a direct energy conversion devices, and even in thermoelectric, also it is a preferred direct energy conversion for the small scale unit. compared to other methods. The solar photovoltaic panels are having some disadvantages, limiting the user due to its higher cost and low load factors. So load factor value, it's very less for the solar photovoltaic, since it is going to operate only in 6 hours or 8 hours compared to 24 hours in a day. There is without storage things. Then reason advantages are advancement in the semiconductor materials, since that all thermoelectric material is made up of thermoelectric modules. Semiconductor materials used the main material for development and fabrication of thermoelectric modules are cost effective when compared to photovoltaic cell, because of this decreasing in the cost semiconductor material. The thing is, photovoltaic cell, it's need a high precision manufacturing process, but the thermoelectric models can be fabricated in local powder metallurgy concept, very simple in foundry and forging. The concept, the construction of thermoelectric model is very simple compared to photovoltaic. That's what that manufacturing cost is very less in a thermoelectric model. The cost of the thermoelectric model is coming down. So compared to the photovoltaic also it's coming down, but compared to thermoelectric, photovoltaic thermoelectric cost is very less. So we like to go for what we call that in some integrated energy system, whatever you mean to say, the terminology which is used for the hybrid or integrated, or in attaching with one system with another system is hybrid. For integrated energy systems, the existing standalone power generation systems and individual system gives lower energy efficiency. So the solar photovoltaic panel about 10%, where solar hanging system less than 15%, and this Stirling engine less than 20%. The integrated energy systems gives higher than the standalone system when comparing it, since it is an additional system is giving without any additional heat input. The many research work, it is an under outlay, under in pipeline, a different combination of energy systems to develop the cost-effective and energy-efficient integrated energy systems. The integrated thermoelectric generator incorporated with an existing energy conversion system from the solar photovoltaic or solar cooker, or what you call it, and LPG cooker, or any heat recovery. If you integrate the thermoelectric, it is in future clean energy conversion and impact on the environment damage, how it is going to be impact. So these are the background of the things, but I like to go for the fundamentals also. Here, the direct energy conversion devices, there are groups, there are many components, many systems are here. It is classified as solar photovoltaic, piezoelectric converter, thermoelectric converter, thermionic and thermophotovoltaic converters. So we are focusing on thermoelectric converters. So other point we are not discussing here. So what is the thermoelectric converter? Its special features compared to other things. So losses are very less in a conversion. It is more efficient and very flexible in systems. So thermoelectric conversion technologies, the current thermoelectric conversion efficiency usually too low to compete with dynamic technologies for the standalone systems. The current thermoelectric materials power is giving 8 to 15% against the 25 to 45%. The cooling COP is 3 times lower than the typical compressors. Then advanced thermoelectric material cools in the next 3 to 6 years when the power 20 to 30% efficiency, where average EJT. The EJT value I like to tell you in the next couple of slides. So what is the importance of the factor of EJT? It is a power factor value. So is average EJT value of 2.0. Please, you can, other participant kindly note down this, what you call the value of EJT here. The cooling, it is a 2 times to 5 times increasing in the COP compared to current. What is an advanced thermoelectric materials cools? It is in better. It's a development of what you call it thermoelectric materials. So it is attracted for the many number of applications because of the features, because of the thermoelectric material. It is a small scale standalone power generation and cooling system with an integrated system. And even in large scales with miniature devices and many applications. So we are coming to the basics of thermoelectric. It is a CFEC effect. It is in 1921. It's a Thomas CFEC is discovered this effect phenomena. It's very well known. It's we might be studied in the physics also. We were 10th class and +2 classes, where the two dissimilar material, metal A and metal B, it is connected in two different temperature difference. It is a hot junction and cold junction. This effect, this difference of junctions on different two dissimilar materials, it's going to be develop a voltage difference. This voltage difference, because of what we call the CFEC effect, this CFEC effect was discovered by the Thomas Sieber. This is direct energy conversion. Thermal to electricity, it is going to be converted. There is no another form of stages of conversions here. So it is the schematic diagram where in this pictures is very clearly shows where the heat sink and heat source. The heat sink will be maintained at low temperature. Heat source is maintaining at maximum temperature. Because of this physics phenomena, it's going to be electric voltage is going to be generated. So thermoelectric model, which is what we call the CFEC effect, it is working all the thermocouples working on this CFEC effect, where you may say one end is exposed to low temperature, another one is exposed with the source temperature. Probably it is going to create voltage difference. This is the same typical power generation in a conventional mode. How that it is an isometric view, probably you can understand very clearly here. P and N junction material, like material A and material B. Material A and material B here. So these materials are connected in a series. It is electrically connected in a series and thermally in a parallel. Thermally, it's a cold side and hot side. This connected in what we call the it is electricity which is going to be generated here. It is what we call the direct current, where in a positive and negative node. Then what is the dimension of this what we call the thermoelectric models dimensions? It is a 5 centimeter into 5 centimeter maximum. 5 centimeter in 5 centimeter devices, which is going to be generate 20 watts of electricity. So if you think that dimension of photovoltaic cell, photovoltaic models, it is a 5 centimeter in 5 centimeter, we cannot export 20 watts of electricity. So this is very what we call it is compact in nature, that is more attractive. So we will see some couple of videos also is there at the end. I will show where it is going to be important. Please, you can understand very easily. So here it is. So I mentioned here where the figure of merit value, it is the function of, yes, it is the CFEC coefficient of the CFEC coefficient of thermoelectric material property, where K thermal conductivity, then electrical resistivity of this material. Where what are the different thermoelectric material which is going to be used in these industries here? Bismuth telluride, it's a first generation of what we call the thermoelectric material generation type, where it is a low temperature applications, where up to 300 degrees centigrade we can work, where the Li telluride is in high temperature applications here, or medium temperature application, where zircon, germanium, and bismuth antimony. And there are material scientists that developed another couple of what we call the thermoelectric material also. It is not listed here. We will see in that some graphical representations. What the Fessel understanding Fessel features in this, the reliability of the power generation is definite, it's confident. There is no moving component in this system, so it is very silent. So there is no moving component, it results there is the absence of frictions. So this dimension of this, what we call the size of this thermoelectric model, it's going to be vary from depends upon the number of thermocouple which is connected here. This is what we call the 1, 2, 3 rows are here, and 2, 3 or 5 rows are here. If you add number of rows excess, then this size also is going to be varied. So it is called some flexible in size. If you reduce this material, what you call it in junction, BN junction sets, then size also it's going to be decreases. So it is known factor. There is no combustion in the system, so there is no emissions. I said here, please have a look on this, all the participants. Please have a look on this graphical representation. Some of the questions may ask at end of your course from this slide only. The bismuth telluride, it is a material lead telluride alloy, silicon germanium, lanthanum telluride. I think lanthanum telluride was not included here, but it is included in this graphical representation. So lanthanum telluride, it's a high temperature applications. So if you look at this high temperature application, silicon germanium, these two combination, it is in high temperature application, but EJT value, it's very nominal value. It is less than 1. But EJT value, its maximum is what you call that lead telluride alloys. So in the blue colors, so lead telluride alloys, it's a maximum EJT value, it's going to be at 1. Close to 4 when the temperature is going to be reached at 450 degrees centigrade. When again the temperature is going to be dropped, then it's a problem. So it is a 1960 developed what you call that in bismuth telluride. It's having in what you call that in the property value, it's very less compared to the recent one. Where the thermoelectric models, thermoelectric generator efficiency, it is defined as a function 1 minus source temperature, sink temperatures, where some factor which is included here. So probably 1 minus this temperature difference, or what you call this ratio, we can say it is called Carnot cycle efficiency, where other terms it is called as an thermoelectric material efficiency. The Carnot cycle efficiency and thermoelectric material efficiency, it is results of thermoelectric generator efficiency here. So I will give you some detailed explanation in the next slide. Probably it will be clear understanding. Yes. Yes, it's clearly mentioned where the heat source, we can easily calculate the thermal conductivity of thermoelectric material and temperature difference. Where the heat sink, we can simple mathematical formulas here, where amount of heat which is out of this heat sink is received 1 minus maximum efficiency of what we call the conversion stage and amount of heat input at TC temperatures. It is a heat sink which is available at the thermoelectric generator side. So we can estimate the maximum efficiency or thermoelectric generator efficiency. It is in Carnot cycle efficiency and thermoelectric material efficiency. Carnot cycle, this efficiency probably might be received 1 minus TC minus TH. This thermoelectric material efficiency also we discussed in the previous slides. So where the best experimental value, it is demonstrated that the maximum EJT value it's in 1.22, but at present what you call the report literature is saying that it is reached a maximum of 3. When this EJT value is going to be increases maximum to number of 3, this thermoelectric material efficiency is going to be improved better. Once this thermoelectric material value is going to be improved better at the value of 1, the complete ratio is equivalent to the Carnot cycle efficiency, you mean to say it's going to give the better efficiency. Once this thermoelectric material efficiency, this value is more than 1, so probably this symbol equation is going to say this thermoelectric power generator, it is going to be dominant in the world compared to fuel cell, better than fuel cell. So the people's the thermoelectric material scientists, the specialists, they're working on development of this EZ2 value maximum 4. Once this maximum 4, it takes another 4 years or 5 years, we don't know. So depending upon the potentiality of the material, semiconductor material and the newer material, definitely hope this thermoelectric material efficiency is going to be improved. The result maximum thermoelectric generator efficiency is going to be dominant in the world. So we will see how that it is going to be work. Here in this some conversion application, what you call the 10 things I like to explore in a better way. So this what you call the 10 isometric view of thermoelectric generator. It's clearly mentioned here how it is connected. This portion. 8 minutes. Very urgent. Huh? You see that. So after 12:30, there is a class. Thank you. So heat absorbed, the heat rejected. So where what you call that the substrate, it is what you call that not an insulator, it is not an electrical conductor, it is a thermal conductor. Where the substrate material, right? The thermoelectric material, what you call that this it is not an electrical conductor, it's only the thermal conductor. So generally it's an aluminum material they used. Right, so how it is connected by metal interconnect, so P and N junction material, it's very simple in nature. So if you explore in better material, you can understand. So really it's a thermoelectric generation is going to be an important topic. Where the thermoelectric devices is acting as a cooler, the power generator or thermal energy sensor, it's various application, various side, it is going to be work as a cooler. Even in what you call it, and power the cooler which is working on a Peltier effect, where the power generator is working on what you call it, Sifek effect. We are talking about only on the power generation side. Our thermal energy sensor, it is also working on what you call it, micro scale energy sensors. The applications already also I mentioned here, but here some of the applications in this military applications, where in aerospace application, the military application in the summer and winter, probably the people are living in a too cold temperatures. It's a minimum of 10 degree, 8 degree temperature. It's northeastern side. So the surrounding temperature, environment temperatures, and making your body, between the body and environment temperature, there is a temperature difference. That temperature difference is going to be help you out what you call the power generation using this thermoelectric generator concept. Even in aerospace, where the rocket engine, so the rocket engine exhaust, this thermoelectric generator is going to be fixed. The waste heat from this rocket engine, it is used for generation of additional electricity. Where the instruments, many instruments where the electricity is going to be used in what you call the standalone system, it is going to be activated. Where the biological system, even human body, in the internal human body or internal any animal body, so where there will be the temperature difference between the muscles and what you call the bones and other things, it can be that waste heat can be used in the biological system also. The medicine and industrial and commercial product, the thermoelectric generators, wherever the temperature difference is possibilities, this application, this thermoelectric application is going to be dominant. So how now we are looking into the thermoelectric model in details, how the thermocouples, probably you can clearly visible this diagram. So thermocouple, or what you call the it is a length element. So it is on one leg, two leg, three leg, it is a P or N junction material which is connected here. In connected this point, probably you can, it is in space allotment, the development and fabrication of thermoelectric model also. Once it is developed, this thermoelectric model, you have a look on this, it is a 5 centimeter, probably particular material. So if you, it depends upon the number of thermocouples which is connected in series here. It is a number of thermocouple is decreased based upon this dimension. Dimension equal to 0.95 mm or 1.6 mm. This dimension is going to be vary. So this capacity of the system also it's going to be vary. One, this geometry, it is going to be decided. It is going to be designed for the final value. So we can develop the thermoelectric models here. So it is a typical thermoelectric model. Then again, we like to have on a very clear pictures here how it is an output voltage, where it is in plus and minus, where the bottom ship at TS temperature or TC hot side, or in a, it is a hot side, where TC is a cold side, where this cold junction, it is a hot junction, it is directly connected, it is thermally connected, and P and N junction material, which is already mentioned in the previous slides here. So it is the thermocouples connected in electrically in series and thermally in parallel. So this what you call the thermocouples, this one couples here connected electrically in a series and thermally in a parallel. Thermally in parallel, it is a hot junction. Then another one is bottom side, it's a cold junction or heat sink or heat source. Okay, that's what it's mentioned in this. This is some the basic arrangements. I like to skip it over here. So now the thermoelectric generator, how it looks like, what do you call it, and if you want to go for testing of this thermoelectric converter. So it is very simple sketch. You can also have a look on this, what do you call it, and it is an heat sink side where inlet and outlet 2 ports for making this arrangement of making this what you call that and heat sink at cold, then water which is going to be circulated on this port, and what you call it a liquid plug or liquid fluid which is going to be circulated. So to extract the heat, one the amount of heat at hot liquid plug or what you call it, and you may say heat sources here, it is going to be transmit the heat to the heat sources of what you call it an PN junction material, where the cold side, the amount of heat which is coming transferred from this one by the metal contact, it is going to be removed here to maintain at sink temperatures. So further, they are using a what you call the liquid phased cooling systems here. Other things, everything it's supposed to be what you call the connected, in tightly fixed. It is a sandwiched. For that, it is using what you call it in some fixtures. The fixture is going to be fixed tightly between these heat sources and heat sinks, and in between what you call the PN junction material or thermoelectric converter, where its complete setup is connected with what you call an insulator. The heat should not be leaked out. So this is simple arrangement for testing of thermoelectric converters. So probably if I show in a video something like, we can understand much more better. So this also some of the pictorial representations for 500 watt thermoelectric power generation system, how it is going to be connected. It is very easy to understand. The component data acquisition system, where the thermocouples, where the thermostatic water bath circulator, the cold water is going to be circulated here, where the thermoelectric generator is connected in this point, where hot junction and cold junction. So hot, it is going to be circulated in this unit. This is an arrangement, it is already done in a research work, how this cold water is going to be pumping in this circulate using this pump, right, using this pump here. So multimeter for the electrical to measure all the electrical parameter, it is going to be used. All this parameter which is going to be a parameter which is connected and stored in a data acquisition system to in the digital forms. Some of the tests were in the previous case, it is in 5 models which is going to be tested, and the result it is presented in this. I think this is in literature studies. It's clearly mentioned what we call it power cost ratio for the thermoelectric material. For power cost, the cost of power per unit cost, it is mentioned in this with respect to the time. So you can have a look. So where the model 2, no, so that representation is not given in this. So it is the parameter where we can give more concentration on what you call that. Model 4 is giving better cost per ratio, power per cost. The cost for power at model 4, which is going to be give better value. So here some of the things, here it is in what you call it an electronic component, how that electronic component heat which is going to be, the heat is going to be taken out and it's used for power generation. Probably if you are open your laptop, the laptop, there is a motherboard, there is the motherboard, immediately it is an electronic component. The electronic component, when it is going to switch on, this electronic component is supposed to be cooled. Further, they are using some cooling fan. This cooling fan is powered by the external sources. But so some of the work is already developed here. This electronic heat, the electronic board, which is going to be generate some amount of heat, that heat can be what you call that and used to develop electricity. That electricity can be drive for this fluid, the fans. It is a self-made circulating system. Some of the things it is also what you call the literature review papers. Know this now. We like to coming into the recent literatures, the hybrid system of thermoelectric generators and its concentrated radiations. What the pictures is going to be says about A, B, C. The concentrator as a lens for one for the sun tracking systems. Then the subdivision B, it is for the different different nodes at the point where it is going to be manual tracking or an automated tracking here. The components, the 6 is a solar radiation, where 5 it is a solar PV panel. So this component, it's the solar PV concentrated solar PV panel is removed in this one, where number 3 and 4 it is a heat extraction system. 3 and 4 is a heat extraction system. This is another combined system of thermoelectric generator with concentrated solar energy. It is also the paper is published. They are integrated with Fresnel lines, then thermoelectric generators and heat spreader plate and heat pipes. So main function, it is what you call the main concentration, main attention, main objectives in order to enhance the power generation capacity. For that, they are used the Fresnel lens, the thermoelectric generator, and heat pipe. Probably the people might be used in what you call the Fresnel lens. It is used for water heating or heating application, or in the commercial in what you call the solar drying application, agricultural product drying application, where the Fresnel lens is going to increase the temperature of working temperature of the stream, working temperature of the fluid. So here this arrangement, it's happened here. What you call the it is a water storage tank, where the heat pipe, which is going to be generate amount of heat, where it is develop the hot water or thermal hot water for the thermal processing unit. The combined system, which is already discussed in the previous slide, that is a schematic diagram, where here it is an experimental diagram. So experimental diagram, it clearly says that there is a heat pipe, it is in copper, it is in a copper heat pipe, which is enclosed in an acrylic tank, 450 ml volume. It is a half liter. So 1 liter, sorry, 500 ml. So 500 ml, it's an half liter only. This volume of the tank, after decreasing this what you call the pipe diameter, it is only 500 ml. It is a small scale unit. Probably if you have any interest also, you can try to do some similar kind of work with the different materials, different what you call the fluids. So how that performance is going to be varied, that you can try. And similar to the coating of this pipe also, that can be done. It is where the sketch, it is an experimental diagram, which is what you call it shown in this different views, where in a top view, where in a side view, how it is looks like. This may help you what you call it and think further on your research work with a different dimension, different geometry, different material aspect. Probably it may help you out. So in this previous slide, so we given some of the things in a factorial representation, but what the specific properties, how that the things are taken into the consideration. Number of thermoelectric couples for in a thermoelectric generator is 127, but what is the maximum power output it is coming at is a 5.7, but the material which is used for alumina, that is a heat sink and heat source material. The property value, it is going to be vary from thermoelectric generator to thermoelectric generator. Even in some of the thermoelectric manufacturing unit, They are given maximum up to this 5.7, it's 100, sorry, 20-25 watts. So it is an American company, HIZ. So that if you are interested, you can also have a look, buy one or two thermoelectric models, and you can do your project work, or you can do your what you call that, some innovative work. So it is a good topic. So good what you call that, domain to do some further work here. Even in this what you call that, the variation, the performance variation of this experimental setup with reference to the water temperatures, how it is looks like, and with respect to voltage and electric power. Probably it is terms which is connected for electric power. So here the power generated by the single thermoelectric models, where the power generation model is, we said it's a 5.7 watts. So things with respect to the resistance, the resistance, where it is a maximum, when it is in 5 ohm, the maximum power at 3.5 watt we are receiving it, when the temperature of 150 degrees centigrade. If this, the temperature difference, it's in 200 degrees centigrade, probably it may reach up to 5.7. 5.7, when the previous case, the specification, it's clearly mentioned here. When this temperature difference equal to, what you call it, 200 degrees centigrade, yeah, temperature difference is 200 degrees centigrade, it is a 5.7 watts it's going to be achieved. When this 150 degrees centigrade they are used, its maximum power output, it is in 3.5. For what you call the resistance value, it is in 4.5 something. When this temperature difference is decreasing it, so decreasing it, then this power output also it's going to be decreased. When if you want to increase this power generation, sorry, the temperature difference, probably it may reach maximum up to 200 degrees centigrade, where 5.7 watts is going to be achieved in this thermoelectric model. Here another couple of what you call the review things. Here this hybrid photovoltaic thermal system with thermoelectric generator. Many work already integrated with photovoltaic and thermal system, where the excess heat of the photovoltaic cell is going to be taken out for the thermal fluid in the form of air or in the form of water. It is for what you call hot water, or for the hot air, it is for the drying application, or for another commercial applications. Probably this combination probably might be seen in the previous many reports, but this report is adding this with thermoelectric generators and non-concentrated solar radiation. It is for the water circulation, it is mentioned, where point number 1, it is a solar collectors. Number 2, cell fax electrode. Number cell, it is a cells fax electrode. Generally, it is called as a detler. So some technical term. When again in the detler in the backside, they are used for what you call the thermoelectric generator. Number 3. Then heat extractor. How the heat extractor is going to be come here, when the solar radiation, solar PV cell is receiving the solar radiation, and it's going to be generate what you call it some electricity, but some of the heat in this back electrode, which is going to be transferred to this hot side of the thermoelectric generator. Then hot side of the thermoelectric generator, this circuit which is going to be generate some amount of heat. Probably this heat sink, it's cooled. Heat sink is cooled using this cold water which is coming in here, and it's cooled here. Then this what you call the difference, this temperature difference, probably it is in 40 degree or 50 degree, sorry 50 degree, where this temperature what you call that, this what you call that 30 degree or 25 degrees centigrade of hot cold water, this temperature difference which is going to be generate additional electricity, it is in 1% or 2%. That is what you call the work is reported in this particular paper. It is also one innovative talk. Even in 0.1% improvement in the performance, it gives what you call that attention at energy point of view from the all the researchers. So here again, I like to give some what you call the 10 fundamentals. We like to skip it here. So already we discussed. This something on the hot heat transfer fluid and cold heat transfer fluid, some mathematical skill. It is mathematical formulation. We can also skip it here. So here where thermophile or heat collector, how the model is going to be generated. Same flat plate solar thermoelectric generators. So we like to skip here. It is not what you call the flat plate solar thermoelectric generator. Only on what you call the solar radiation, which is striking on this hard side of the what you call the thermoelectric generator and gives what you call the power output, where the heat sink it is used as an what you call the radiator. Radiator means it is an air cooled heat sink. Where the schematic diagram of multiple solar concentrator. There are many solar concentrators which is striking on this hard side. We can also skip here. This is also one of the work the people already published. Now another one is we like to work for another one is the reported with micro energy harvesting based on the thermoelectric and latent heat effect. What is the micro energy? What is the value of micro energy? Where 1 watt, so 10 power minus 3 watt, this is microwatt. So in 10 power minus 3 microwatt, how it is going to be work? Some work already reported in sensor and actuator international journals. They're using what you call the term solar micro energy harvesting systems. So this picture is clearly showing that where it's a 45 mm, it is a 4.5 centimeter only, 4.5 centimeter. So how that phase change material, it is an encapsulation in what you call it in some element material, elemental metal strip here, and the structure, the fourth structure, it is called as in 4, where all insulation material, what you call PCM material, phase change material is going to be filled here. Where it is this total container, it is connected in what you call the PCM container. So total whole setup, it is an insulation material. Where we can have a look on what you call the thermoelectric generators on this point. This thermoelectric generator is directly embedded with what you call the PCM container. Right? It is on cold side of this thermoelectric generator is connected with PCM container. The hot side is directly, it's a spotlight 20 watt lamp. It's going to be given what you call the light. So this radiation which is falling on the hot side of the thermoelectric generator, now the properties, the variation of the properties is going to be stored. All the operating variables is going to be stored in a computer through data acquisition systems. Where this what you call the spotlight of 20 watts, which is going to be so lighting energy to the hot side of the thermoelectric generator. How this performance is going to be varied, so we will see in the next slide. So that is what a schematic diagram here. So where this is what we call an experimental diagram here. Then this experimental diagram where this graphical representation is shows what we call the temperature variation on the cold phase of the thermoelectric generator with PCM and without PCM. This schematic diagram, what we call that the photographic view clearly shows that the work unit with PCM. This small box which is going to be say it is called as a unit with PCM material. Another unit so with heat sink. With heat sink, it's an air cooled heat sink, right? Air cooled heat sink here. Now this performance, how the variation with respect to the time, what will be the temperature, how the temperature of the heat sink is going to be improved, whether it's decreased. When if you want to keep your heat sink always minimum temperatures to maximize your thermoelectric performance. Look at here, when the temperature is time is increases, the temperature of the PCM is always decreases. It is at minimum temperatures. Where in an air-cooled heat sink, the temperature is going to be increases. So when if you are maintaining that heat sink at minimum temperature, so as a result in the experiment, what you call that small mathematical correlation we shown in the earlier, this performance of the thermoelectric generator is going to be improved. So let me go on to the next slides. Probably these all the things which is taken from that particular journal papers. You can have a look the voltage generation with the times, where the voltage generation between what you call that with PCM and without PCM, that with PCM the voltage generation is maximum, compared to without PCM. So without PCM is a light color, with PCM it's a dark black color. See, the voltage generation is giving the maximum value. No, at point where what do you call that, maximum value up to at this 3 hours time, then voltage generation is going to be little, what do you call that, it's dropped at the time after 3 to 21 hours. The reason is, so we will discuss here. Where this, what do you call it, harvested energy. The harvested energy, so that is our ultimate aim. The harvested energy with PCM and without PCM, this harvested energy in joules, it goes, what do you call it, the maximum here compared to what do you call it, minimum at PCM. It's harvested energy minimum, without PCM it's only 0.002 or 0.03, but with PCM harvested energy is maximum.
Excuse, sir.
Please.
Sir, this is applicable for what application, sir? This system.
This is for sensor. It is for the sensor application where your transmitter want to work, where there is no electricity. So how we can generate electricity without, what do you call the term, with available resources.
Okay, sir.
Sorry. Yes. So this diagram is a schematic diagram where you can easily clearly understand what is the basic concept which is happening over there. So here there is the solar radiation which is directly falling on this hot side of the thermoelectric generator, where this bottom heat sink side, it is attached with the PCM. The PCM is going to be collect the heat, rejected heat from this heat sink and store it in a PCM, and this temperature difference. This is hot side and cold side, where the high temperature, low temperature. Once, what do you call the time, this is going to be happen during the solar radiation, when solar radiation which is available. When the solar radiation is not available at night time, you mean to say after 6 o'clock. After 6 o'clock, what happened that the surface at heat source side, it is going to be decreases, where the PCM, it is a heat sink, now it is a high temperature. Now this can be acted as a reversed way. So the electricity is going to be generated. It is, they already done at some micro level. If you want to go for what you call the 10, it's 100 watts or 200 watts, you can also develop with a new modification of dimension and geometry and materials. Probably this is a concept or same, very simple and same, right? So now both the convection, this is radiation takes place, where in the night time it is a convection is going to be takes place. Now the amount of heat is going to be transferred from the heat source to, sorry, this act as a heat source and this act as a heat sink. But in the night time, so daytime it is a heat source and heat sink. Because of this temperature difference, this system is working 24 hours in a day compared to your solar photovoltaic cell. Solar photovoltaic cell can work only in radiation in the daytime, but it cannot work in the night time, in the reversed way. So that's why this solar thermoelectric generator is giving a better option with additional heat storages. Now I like to give some, I think this is, this concept, it's already developed by our peoples. It was in a previous, I think the literature is clearly showing that when it is going to be started, where they are used for solar flat plates thermoelectric power generators. The time it was plate temperature is received 70 degrees centigrade, the receiver surface is only 0.1 meter square. Overall efficiency, it's taken only the 0.7%. So there is no photovoltaic cell. So only what you call the flat plate thermoelectric generator. So it gives what you call the overall efficiency, electricity, it's only 0.7%. Very low value. Now better, the later some development was happened. They added one concentrated aluminum, what do you call it, aluminized polycer reflector and this acrylic cover. They got what you call it, some improvement, 0.1 meter square, where the overall efficiency could reach to 1.2%. where the receiver plate temperature also is reached to 100 degrees centigrade. So compared to the previous slide, 70, here it's 100 degrees centigrade, but the overall efficiency also is reached to what we call it 1.2%. So this is what we call the 10 available literatures. Then another concept which is happened here, it is in solar parabolic trap thermoelectric power generator. Probably you might be knowing it is a trap collector and parabolic disc concentrator. The trap collectors, they are used here. They are taken what you call the thermoelectric devices. This is a receiver component. Where in the right hand side it's a subdivision B, it is a receiver component. Where you may say it is in the right hand side, which is showing that the receiver component of what you call the concentrator plate, where the thermoelectric devices is fixed over here, and the observer plate. So probably you may say it gives what you call that better efficiency. Since the operating temperature of solar concentrator is maximum. 1 minute. So where the observer plate, and this in the right hand side, you can have a look on this observer plate. In this observer plate, it is a thermoelectric devices is attached. This definitely this observer plate is going to give the maximum temperature more than 200-300 degrees centigrade based upon the concentration ratio of the solar trap collector. This is some report. It is an American Society of Mechanical Engineering. They developed a system which air-cooled heatsink, where this thermoelectric generator cold junction is maintaining at this temperature, where it's a hot side. The hot junction is powered with compound parabolic concentrator. Compound parabolic concentrator, parabolic trap concentrator, and parabolic disc concentrator. They are in 3 different in a geometry. Please have a don't confuse with them. There are in 3 different in a geometry. So where the copper heat spreader is provided here, where the maximum temperature is going to be received here at 190 degrees centigrade. The receiver surface also maintained at 1.2 meter square, but overall efficiency here is improved at 2.2%. So once what we can understand here, when the high concentration or high temperature, so this efficiency definitely is going to be improved. So this is an arrangement. This is already done the job. Now another concept here. Sorry. Yes. So it is in photovoltaic and thermoelectric conversion, where the solar radiation which is going to be concentrated and falling on the solar photovoltaic model. The solar photovoltaic model and thermoelectric model is physically attached, where you will get both electrical terminal. The heat is going to be rejected. This is one way to improve that efficiency of the solar photovoltaic system. Whatever the solar radiation which is falling in the solar photovoltaic model, which is going to be transmitted through what you call the thermoelectric model, and the power, it is an additional power which is from the thermoelectric model, is an added advantages here. Where another arrangement, how that solar separated, where earlier case solar photovoltaic and thermoelectric physically attached. Is there any possibility to separate between solar photovoltaic and thermoelectric? Yes, some work is already reported, where they're taken into that what you call it in how that arrangement is happened. There is a lens. There is a lens here, the concentrator solar radiation is going to be filtered and concentrated on this what you call the water circulation system, where this cell water circulation pipe is heated up. This cell what you call it and heated up, it is acting as a heat sources, and what you call it in the then bottom side it's naturally by natural radiation, it is heat, it is acting as a heat sink. Then some portion left out portion of what you call that in this phase, which is solar radiation which is falling, and the solar PV panel. Solar PV panel, the bottom side is cooled now. It is also one way to improve the solar photovoltaic cell efficiency. Then another way arrangement, what you call it, and increasing the thermoelectric cell efficiency. How they are thinking, they are proposing the system, and they got a publication in the particular journals. So it is one way, what you call it, and you can also think how innovative idea. So working very effectively, this thermoelectric and photovoltaic cell. Probably these people are used water. So if you are using another heat transfer fluid, the similar concept with another heat transfer fluid, so probably the performance is going to be vary. If the performance gives the better result than the present reported, then you can also publish in the journal papers. So this is very basic, simple, what you call it, and even in the rooftop, it is always exposed with what you call the heat. That heat rooftop roof material heat is recovered, is taken as a heat source, and what you call the and bottom side it's acting as what you call the sink. This temperature difference is going to create some electricity. That electricity can used for what you call the drive your power. So it is this is also one way, or you can use it. It is used for the ventilation. Ventilation also it can be possible in this diagrams. So this is also reported in a good journal publication. So this where we did my some work. We used what you call it unused solar disk concentrator. Unused what you call the satellite dish antenna, and we fabricated one parabolic dish concentrator, and we got the thermoelectric models, and using this small sketch we also did some experimental work. Solar parabolic dish thermoelectric generator. This setup was installed at rooftop of mechanical block at NIT Tiruchirappalli. So it is what called the sketch. I think Dr. Sivareddy sir is already visited when he was with NIT Tiruchirappalli. He also supported me a lot. It is a manual operating system, not automatic tracking system. Manual tracker, so it is only 2-dimensional. Then focal receiver where we got it. So this is another arrangement where I mentioned somewhere where this what call it thermoelectric is going to be fixed on the biomass stove also. So this is a simple sketch here where you may say biomass stove. The side of the biomass stove is added with thermoelectric generators, where the waste heat of the side of the wall it is used as a thermoelectric generator hot side, and the other surrounding air it is on cold side. So this also helping us generating some additional electricity, so without any heat input. So where it is a schematic diagram of the things, where it is amount of weighing machine. So probably it is meant to say amount of fuel is consumed, amount of what do you call the biofuel is consumed. We can measure the weight balance method. So we can also measure. So we can also measure all the property value it does and used for the digital display. So this is also one kind of what we call the experimental, one kind of proposed setup. And moreover, it is an application in a thermoelectric for your pacemaker. The pacemaker, generally the person who is in a patient's his heart having the problem, the circulation of what we call the blood, it is not in a normal. The pacemaker is going to be used. It is inducing your heart to activate and pump the required amount of what we call the blood in your artery. So further, the pacemaker is used. But in the pacemaker powered with some battery, The battery is what you call it, an electrical battery. It is a very small iconic battery which is going to be fitted inside it. But the pacemaker life, it depends upon what you call it, battery life. The battery life, generally you aware that it is a maximum 2 to 3 years or maximum 4 years. So what the battery life is going to, the patient is going to be get some inconvenience. The doctor definitely will check the battery life. For that, again, cutting the human body, it's not good, right? So now it is an implantable, it is not implantable devices, it's an outsource. That is an inconvenience to the patients. The problem is here, the battery is a pacemaker battery. Life or the pacemaker can be operated using a thermoelectric generator, using a body heat. Using a body heat, that is going to help what you call it, makes more comfortable with the patients. Whenever the human body is alive, human is alive, it's make what you call it, body temperature is going to be exist. That body temperature is going to be generate electricity that is helps to activate the pacemaker. For this body to what you call it, biosystem or body to what you call it, heat, how it is going to be activated. There are some couple of what you call it, things here, the pictures, which is on this. Have a look on this your hand. It is a bio where it is working on this thermoelectric concept, where your health monitoring with the phone, and you can also have a look on your hand and head, everything. So probably this thermal scanner diagram, it's mentioned where the maximum temperature is exist in your body. So 1 minute. So okay, sir. Thank you for. Now, these were, we are also going to see some couple of slide videos where flexible thermoelectric, how it is going to be handled. So this hybrid PV thermoelectric, I like to skip it over here. So we will move to the next slide. Where same concentrator, PV detailer, and heat sink. We like to move to here. The solar thermoelectric generator assisted with the water pump. This solar assisted heater, which is also used for water pumping applications. So it is an applications are very more. So where the water pumping system, it is was evaluated compared with thermoelectric generator water pumping and photovoltaic water pumping and diesel water pumping. So you can have what are the various components which is involved in this here. When the solar thermoelectric system is a little costly, what you call it, compared to photovoltaic because of additional concentrator, and there is no maintenance, there is no fuel cost compared to other things, whereas the operating hours almost maximum compared to here. What is the cost which is going to be used in these systems? So the development, future development of thermoelectric, newer development of newer hybrid system, different solar collector and incorporated with the thermoelectric generator, and it is also helping what you call it some more. Where the development of advanced materials, semiconductor materials to improve the ZT value, that is a figure of merit value of thermoelectric generators. It is also what you call the future development. Then people can go for what you call the qualitative analysis, where the maximum losses is happen, energy conversion losses. That can be done only on exergy analysis. I think our Dr. Severity is more expertised. He might be giving more talk probably on this exergy, what is the need of exergy analysis and other things. But in the exergy analysis of the component of solar thermoelectric generators, so we can identify the locate where the improvement can be done. The concentrator also can be added to improve its efficiency. So since the concentrator concentration ratio, it helps to improve the higher operating temperatures. Then low conversion efficiency of the thermoelectric generator will be more effective for because of this low conversion efficiency of the thermoelectric generators. We should not operate the system for the higher capacity. We can operate this system for the lower capacity. So these are the developments can be done. So further development of the materials of it is going to be it is going to be done, since it is multidisciplinary in nature. The material aspect, design aspect, and development aspect, and analysis aspect, all physics, chemical, mechanical faculty can work together to for the further development or future development. So let me conclude here on my presentation. After this, I can have some couple of slides, videos that also give some interesting concept. So probably we can, after this conclusion part, we can have a look on that. Then after that, we can have a discussion. The different types of solar power generation technologies are reviewed in this discussions. The cost effectiveness of components and maximizing the conversion efficiency are addressed in the further research. More attention to be made to develop advanced material structure optimization and more practical applications. The global needs for the sustainable and clean energy inspire the great excitement. There are more excitement in this field. Then innovation of the reviewed technologies can meet the energy conservation and environmental. It's a spelling mistake. It is environment is going to be product. So this is my presentation on this. I like to show some slides. So please have a be wait. Let me where the flexible systems. I think my screen is visible to you, my videos. Hello.
Yes, sir. Desktop is visible. Okay, you can play the video. Now it's no voice.
Videos are not playing. Earlier it was played. Okay. No, okay. No, it's coming. No, this video is coming, na? Arre. Okay. I think we need to what to do. So I am screening. No. I am sharing the screen. But the video is not screening. Now the screen. Okay, thank you. Okay. Ready, Garu? Okay. Thank you. So here, sorry for the audio issues. This person is explaining about the flexible flexible thermoelectric power generators, where he is mentioning about how that flexible thermoelectric generator. Now have a look here. So he is making what you call that and how it is flexible. All this thermoelectric concept here, the material which is shown, same our material which is shown in our PPT, all what you call that in semiconductor material, PN junction materials, which is mentioning here. He is talking about what you call that and how it is going to be connect. Without battery, you can operate your computers. So the battery, there is no battery, but the system which is mentioned in this components here. Ek minute, how this to play? Yeah. So he is talking about what we call an electrical watch, and then flexible material which is used for your keep it in your like a wristwatch. The electricity can be generated. It is for what we call an operate your watch or operate your what we call that electricity can be generated for other electrical sensors. So that's what he is mentioning here. Where this topic where what we call it an your flexible thermoelectric generator can be is fixed here in this small element. So he is saying that so mostly it is his company project, but is mainly concentrated on what you call it flexible thermoelectric power generators. So we will move on to the next slide. We'll move on to the next slide. Is it visible? Audio is coming?
Audio is not coming, sir, but visible hai.
Arre. So here, yeah, so there is a main problem here. Here some of the basic experiment about thermoelectric power generator, how it is playing. So what do you call that in this experiment where in wax which is giving input, even in body heat, they're taking what do you call that in things, how the temperature, what do you call that in voltage is going to be generated with the thermoelectric generator. So man is keeping on what you call it in Peltier effect. So how it is going to be generated. So in this Peltier effect also experiment how that ice is going to be formed. So it was, he is mentioning about so much what you call that material. So different material, how that property value is going to be changed. Even in what you call the small experiment using what you call the cigarette light, they are heating on the hot side, the temperature voltage is going to be generated. Even in other side also is checking at how this variation is going to be very small what you call the thermoelectric generator. when we can apply what you call the hot side of what you call the our solar concentrator on this part. So this is going to give what you call the electricity. It is very simple in concept. Where it is a sink, it is an air cooled heat sink. It is mentioned in this diagram here. It is an air cooled what you call the things materials. Sometimes when we are using what you call the hot burn, it's a problem. So here they are developing about what you call the two thermoelectric models. It is attached on what you call the heat sink. It is going to help us a small experiment. It's already started. They made it what you call the heat sink thermoelectric. So this is a heat source. Probably now it's burning it. So how it is electricity is going to be generated. The this fan also it's going to be used for drive this fan, small fan. Now it is this when all the parameters is connected here. The what do you call the this is you might be paste thermal paste in order to fix heavy tightly fixed thermally. Now this is for the solar concentrator. What do you call the solar concentrator based system? It is a small fan. It's going to be small concentrator is fixed and it's touch on this what do you call the thermoelectric cell. So have a look. So it is a small what do you call that experiment. When the temperature is going to be dropped, it's going to be decrease its electricity. Same whatever it's we did the work. Here it is a Peltier model. When one surface is cooled with an ice, small experiment. I think this video so is discussing about what you call it and same thermoelectric models. Some handy exercise. He used what you call the thermal scanner. How where the thermal scanner the temperature is going to be maximum, minimum, everything is doing what you call it in this small exercise. So small what you call the lab scale model what you call the is developed. I think almost. So he developed what you call the other couple of 6 models how we can integrate. He is developing what he want to do. It's a 6 models which is talking about what you call the heat sink performance, how it is going to be work. I will send all these video clips to all the participants along with the PPT materials. So we like to close it here. So if any questions, if you have any questions from the participants side, please you can ask. I think I completed the 20 minutes before. Now we can have a questions. Thank you, Ritigaro. So
Yes. Thank you, sir. I think nice presentation regarding thermoelectric generation.
okay, I think anyone is covered on the thermoelectric. I am not aware of that.
I think a majority background is mechanical and humanities, sir. Physics background is there. Mechanical and physics, electrical.
Okay, sir.
I think you are the first presentation on thermoelectric generation.
No, that's what my concern, because some of the people are working on a thermoelectric also.
Yes.
So whether any speaker resource person is
No. You are the first speaker, sir.
Anyway, it is new to all the participants.
Yes.
So that is some information supposed to reach. When you are connecting me through online from Nandyal in Rajiv Gandhi Memorial College of Engineering. So almost 36 participants are in line. Let them have look, let them have what you call that, some idea. So probably there's a flexible thermoelectric concept. People are working, even in TST is giving some of the grant to what you call that, PMS College, and even in IIT Delhi and IIT what you call that, in Mumbai, the people are working on the development of the thermoelectric materials. So this, I think this talk can give some initiation to the participant to work further on this topic.
Yes. Sir, same link is available on YouTube also, sir. YouTube also parallel it is coming. In YouTube also some participants are there, sir.
Okay. Oh, good.
So now session is open.
For the
Participants,
discussion.
you have any doubts, you can unmute yourself and ask expert with us. Utilize the opportunity. I think.
Any questions? I think.
Maradega sir చెప్పింది. మరందే లేదు నేను ఆర్డర్ చేసుకున్నారు కానీ రిటర్న్ వస్తే లేదు సార్.
Someone is saying that.
Hello, sir. Good afternoon.
Good afternoon, sir.
Sir, can you tell me what about piezoelectric material? Is it also comes into thermoelectric?
No, piezoelectric is working on the different principle. No? So we are not talking about the piezoelectric. The piezoelectric is working on what you call it, fixation of the sounds, fixation of what you call it, and the.
సార్ చాలా లాస్ అయ్యారు, అసలు లోన్ తీసుకున్న పర్పస్ తెలియదు.
So we are talking about only on a thermoelectric.
It is shown here.
Sir?
At a distance of 24 and exactly 12 mm on the left side as well as right side.
What, sir?
Sir, that is not some other chat, sir. Sorry for the inconvenience. Any other participants? In Google search, you can search Ishwar Murthy. Like that, you will get his publications and his contact details. Further, also, you want any support for that? Mata Vaishnavi Devi, very good temple. For visit, also, you will support us.
Sure. Welcome. Our university website. Visit us.
Yes. Thank you, sir. Thank you very much, sir.
Thank you, Reddy Garu. Thank you so much for providing an opportunities on this online platform. We are meeting here. We are supposed to make it as an offline, but the kind of situation is not comfortable for this offline meeting. Anyway,
Yes,
we are discussing. We are meeting each other through online.
Yes.
Thank you so much for giving me an opportunity in this.
Yes, sir. After this, we will send one email, sir.
Sir, just a second. Sir, Ishwar, sir, sir, is there any conference is going on, right, at present in university, right?
Yes. And some energy management HOD is organizing one conference.
Okay, fine.
Please, you're most welcome.
Sure, sir. Because we have submitted papers. Okay, till now we didn't get any response.
I will ask him. Could you send your details by email? So I will forward it to them and I will ask them to update.
Sure, sir. Sure. Thank you.
Thank you so much.
Okay, sir. After this, we will send one email, sir. Please provide your details, bank details.
Okay.
We will transfer regarding.
Okay.
And
no problem.
finally, special thanks, sir, Because after a busy schedule, now you are highly administrative activities you are managing.
No, that is only all files and clerk work.
Yes, no doubt. Thank you, sir. We
Thank
will
you,
use your
Ritika.
expertise in next FDP also, sir. We are planning for February. In February,
Okay.
again we will contact you, sir.
Sure. Thank you, Ritika.
Yes, sir.
Thank you.
Thank
Thank
you,
you so
sir.
much. Thank you. All the best to all
Thanks.
the participants. See
Yes,
you.
sir.
Take care. Bye.
Okay. It is a notice, sir. For afternoon session will start 2 o'clock by Dr. Narendra Singh, Assistant Professor, Department of Chemical Engineering, Indian Institute of Technology, Tirupati. His topic is next generation solar cells. It is important. Why? Because only semiconductors means one or two types of semiconductors only we are dealing. But printing technology came to the picture. So I think he may explain that one. It is more useful for our R&D and getting funds from the DST. So all will join at 2 o'clock sharply. Expert is available with us. Thank you very much.